So guys, what are we doing with these videos?
Well, you and I are going to talk about circuit breakers.
And we're going to talk about something a lot more exciting than that. We're going to talk about contactors.
Well, I got fuses, and you guys know all about fuses. We protect circuit breakers and contactors all the time.
Whoa, this is not a competition.
You mean like the overcurrent protected device games?
Well, breakers would win.
No way, contactors have it all day. The endurance is there.
600 volts, 300,000 amp interrupting rating, and current limiting. Come on.
I think we should talk about all these different types and applications of these products, but I think for contactors, I think we need to focus on the number of operations and that special application of switching the primary of a transformer.
Yeah, I know that's one of your favorite applications. We'll talk about the basics and then we'll start covering that stuff. So what is a contactor and where are they typically applied on an electrical system? A contactor is an electrically controlled switch used for switching a power circuit with a lower power level control circuit. For example, using 24 volts DC to control a 480 volt AC motor. Contactors are typically used to switch high current load devices such as motors, heating, air conditioning, lighting, capacitor banks, and transformer switching that can be controlled either locally or remotely by manual or automatic control devices. Contactors are also commonly used in transfer switches. Generally, when you think of switching power circuits, you may think of circuit breakers, relays, or starters. What is the difference between a circuit breaker and a contactor? There are many different types and sizes of each, but in general, a circuit breaker's primary function is to interrupt circuits during fault conditions, and a contactor is primarily used to turn on and off loads or control equipment through automation. While a circuit breaker could be used to turn on and off the same loads, it would be considered more of a manual switch. Even more importantly, circuit breakers are typically designed for 10,000 operations and contactors are designed for 1,000,000 operations. What is the difference between a relay and a contactor? While both are electromechanical devices and operate in a very similar manner, you can think of a relay as a smaller, less expensive version of a contactor. Relays will generally be used to switch lower single-phase voltages and current levels that may not exceed 20 amps. While contactors can switch thousands of amps in low and medium voltage three-phase systems. What is the difference between a starter and a contactor? This can tend to be confusing because a starter is simply a contactor with an overload relay connected to it for motor protection. This motor control center bucket shows a contactor with this overload protection, which as a system will be considered a low voltage motor starter. Without fault protection, this motor starter could be damaged if it attempted to interrupt fault current, so we include this HMCP to provide fault current protection in an MCC bucket. This AmpGuard medium voltage motor starter uses a vacuum contactor in a relay for overload protection. These power fuses provide fault protection for this motor starter.
Let's take a look at the components that make up a contactor. These would include the main contacts, auxiliary contacts, coils or electromagnets, and springs. The main contacts are the current carrying part of the contactor and are designed to carry a large amount of current. These contacts may be air contacts or inside vacuum bottles. It is very important that the main contacts close and open very rapidly to reduce arcing, but closing the contacts too fast may result in contact bounce and permanent damage, which can lead to unwanted open-close cycles. The auxiliary contacts are a separate set of contacts that are isolated from the current carrying main contacts. These contacts are typically used for low power control circuits. Typically there will be a set of normally open and normally closed contacts available with an option to add additional contact blocks if needed. The electromagnet or coil is the key component of a contactor as it is the driving force for closing the main contacts. By applying either AC or DC current through this coil, a magnetic field is produced when the electromagnet pulls in the moving armature which holds the main contacts. If the coil is energized, the main contacts will be closed and the contactor will be applying power to the load. Some contactors will even use multiple coils, one to pick up or energize the contactor, and then another to hold it closed once it's been energized. Kick-out springs are used to allow the contactor to be mounted in any position. Contactors use over-travel springs to ensure that an adequate level of pressure is available when the main contacts are closed. We mentioned earlier that the life cycle of a contactor is about 1 million operations, but this is highly dependent on whether it is a latched or magnetically held contactor. Latch contactors use a stored energy mechanism similar to the spring used to open a circuit breaker. A reliable source of power must be available to operate the solenoid that opens the latch contactor in the absence of control voltage. Capacitor trip devices, as are used with stored energy breakers, are commonly available to solve this problem. A latch contactor may last for tens of thousands of operations. If the load is infrequently switched, consider latch contactors. Magnetically held contactors have a much longer life, but they do require continuous power being applied to the coil to stay closed. They might be rated for millions to perhaps 10 million mechanical operations. Magnetically held contactors have a problem if their coil voltage drops. This could be caused by a fault elsewhere in the system. Latch contactors solve this problem because they are mechanically held. Vacuum contactors are magnetically held, but may not yield as many mechanical operations due to fatigue failures of the metal bellows.
Whether using a latched or magnetic contactor, choosing the correct size of contactor is critical for proper operation. First, you need to know if you are selecting a contactor for a NEMA or IEC application. The NEMA standard uses a more brute force approach that requires less front-end engineering. Basically, you have this size motor, so you use this size contactor. In nearly every case, the only information that is needed is the motor's horsepower and voltage. NEMA contactors or starters come in a range of sizes from size double-aught to size 9, and for reference, a size double-aught contactor has a maximum horsepower rating of 2 horsepower at 460 volts, and a size 9 contactor has a rating of 1600 horsepower. You will probably never see anything larger than a size 6 except for very unusual applications. So what's different about IEC? IEC allows the engineer to choose a product not just on its ratings, but also its duty cycle. That means IEC products require more front-end engineering. For example, you have to know the duty cycle, or how many times you are going to operate the contactor and how often. And unlike NEMA, which only requires that you know the motor horsepower, IEC requires that you know its full load current and information about the load that is connecting to the motor. This will be a deciding factor in determining if you can use a smaller size contactor. The smaller contactor usually means it is less expensive, but remember, more front-end engineering is required when this is done, and there are more discrete sizes compared to NEMA. While NEMA standards list 10 sizes of contactors to operate motors from 2 horsepower to 900 horsepower, IEC standards have 20 sizes to cover the same range of motors. This is why there has historically been a misconception that IEC contactors are smaller and less expensive than NEMA. IEC starters are typically not designed to be serviced. Instead, they are replaced after a failure. NEMA devices are generally serviceable without removal of the starter from its enclosure or bucket. The list of NEMA, IEC, IEEE, and UL standards that apply to contactors is significant. Here are a few of the key standards that you may want to consider for your application when applying contactors to your power system.
There are many applications where contactors can be applied, most involving motor starting. Even motor starting may require special application considerations. For example, the inrush current for a high efficiency motor can be 12 times full load current, which is significantly higher than a conventional motor, which draws around 6 times full load current. But there are other applications for contactors where special considerations may be required. For example, when contactors are used for lighting control, there may be significant inrush current. This has always been a problem with incandescent lighting, but it's still an issue with LEDs because their DC power supplies have filter caps on the front end that draw significant inrush current. For power factor applications or capacitor switching, contactors can be prone to restrike issues. There may be trapped charge on the capacitor, and when the contactor applies line voltage to this pre-charged capacitor, there could be double the voltage across the contactor. This could result in unwanted restrikes and pre-strikes, which can cause various problems. In addition, significant oscillating transients occur with capacitor switching, so special pre-charged circuits or zero crossing control may be required to protect the system. Although we mentioned contactors being used in some transfer switches, the design and form factor of those contactors are significantly different from the contactors we've mentioned thus far. We won't go into all those differences in this video, but you can learn more about those points here at the PSEC. Finally, contactors are commonly used to energize and de-energize the primary of a medium voltage transformer. The reason contactors are used instead of vacuum circuit breakers surrounds the issue of medium voltage vacuum chop current. Chop currents can cause transformer failures. This has become a more common problem with larger medium voltage dry type transformers that are more frequently switching in today's data center applications. Contactors have lower chop current than vacuum breakers, but also have lower interrupting rating, so must be wired in series with an overcurrent device, typically a fuse. That fuse is designed to take over if the fault current is too high. The big challenge for a magnetically held contactor, though, is during a high current fault, the bus voltage drops, which may cause the contactor to unintentionally open and start the interrupted fault, which it cannot do safely. In a properly designed system, the contactor only opens for lower current overload conditions, and the fuse clears during the high current fault conditions.
Although contactors seem like a very simple device, there are many applications and considerations that you should think about when applying contactors on your power system.
If you want to learn more about contactors, or even fuses or breakers, contact us or your local EATON representative to schedule a visit to the Power Systems Experience Center today.